All right, our next example is sliding around a curve or skidding around a curve. If you take a curve at high speed, there is a centripetal force that is acting to keep you on the road. That force is going to be pointing towards the center, and that force is all from friction, provided that it's a nice even road, nice level road. Friction is what keeps you moving in a circle. There isn't another force acting on you in that direction. So we're going to talk now about how you can make that comparison happen and figure out what you need to do to solve a problem skidding around a curve. So here we have a problem. It says a car of mass 1,240 kilograms moves around a bend of a radius 63 meters on a horizontal road at a speed of 18 meters per second. If the car was to be driven any faster, there would not be enough friction and it would begin to skid. What is the coefficient of friction between the road and the tires? So first thing we should do is just list the variables that we know. We know the mass is 1,240 kilograms. We know the radius of this curve is 63 meters. We know that the horizontal road speed is 18 meters per second, and since that's meters per second, we know that is V and not omega. Omega is radians per second, V is in meters per second. So now we're going to ask, what is the coefficient of friction between the road and the tires? To get to the next step, it's helpful for us to draw a free body diagram. And let's say we are drawing a diagram from the front of the car. So just to be clear, I'm going to try to draw a picture that looks kind of like the front of a car. Excellent. Looks exactly like the front of a car. Perfect. So what we know about this car is there is a weight. So there's force of gravity, as there is with any object that has mass. There is a normal force that's keeping this car from falling into the road, that is R. And there's also a force of friction. Let's say that the middle of our circle is to the left here. So the force of friction causing this car to move in a circle is acting horizontally because the car is trying to turn in a path like this. From this picture, you should recognize that that is a fairly similar free body diagram to what we saw in the rotor problem. That we have two forces that cancel each other out, and we're left with one force that makes up the entire net force that is acting. So this net force, which since it's an object moving in the circle is equal to the centripetal force, is entirely given by FF. That is the force of friction. That is the only force that is left acting on this object. Alright, so we know some information about this setup, and we know some information about calculating some of these values. That we know that the centripetal force is given by a couple different equations. Either, if I go up to the top here, either mv squared over r or m omega squared r. In this problem we don't have omega, but we do have v, so we're going to opt for this first equation. And we're going to say that the centripetal force is just mv squared over r, and that is equal to the force of friction. In this case, force of friction is always given by mu times r, the coefficient, times r, our normal force. Now we know almost all of this information. The only thing that we don't have on our list here on the right, or sorry, on the left, is r. R, in this case, is equal to the force of gravity. Those cancel each other out, which we know is equal to mass times gravity, or 1,240 times 9.81 12,164 newtons. So with all of that in mind, we can plug in what we know and solve for what we don't. We know the mass is 1,240. The velocity is 18 meters per second. And we square that. Divided by the radius is 63. And that is equal to mu times r, we just calculated, was 12,164 newtons. When you plug all of that in and solve for mu, you will find that mu, your coefficient of friction, keeping you on the road, has to be 0.52. And again, unitless number because it is a coefficient. If our coefficient of friction was less than that, and you tried to travel at this 18 meters per second around a 63 meter radius road, you would skid off that road. There would not be enough friction between the tires and the road to keep you going in that circle, and you wouldn't be able to pull as tight of a turn as you need. One way that we can get around that is by banking these curves. IB does not expect you to be able to solve one of these mathematically, so we're not going to use numbers here, but it does say you should understand the idea of an angled curve in a qualitative fashion. So an angled curve, the biggest difference here is that there is going to be something else besides friction keeping you on this road. Our normal force, the R force, is going to be acting perpendicular to the surface. That means that part of that R force is acting in the Y direction. Oh, sorry about that. Acting in the Y direction, we have RY pointing up, and part of that force is going to be acting in the X direction, RX pointing to the left. The biggest thing that means is not only do we have the force of friction acting inward like we did before, but we also have now this normal force, or at least a component of it, we're going to call that Rx, pointing in towards the center as well. So since those two forces act in the same direction towards the center, that means that you can drive at higher speeds than the force of friction can support by itself, while still safely staying on the road. That's why if you ever look at a NASCAR track or ever look at the Olympics when the cyclists are going around that small velodrome, all of those tracks have a pretty steep angle to them. And that's so that they can go around a sharp turn at a very high speed without any danger of them slipping off the side and crashing off the side of that turn.